y'all coming today, and look forward to talking to you and giving you some ideas about the Internet of Things and the low-power WANs, or low-power wide area networks, that I think will be a major contributor to collecting the information. So, as she said, I'm at Hightower. I'm going to go over kind of a brief history so everybody gets a level set here as to what's going on, how we got started. M2M and machine communication has been around a long time. I'll break it down into the components of it, and then I'm going to talk about low-power WANs and compare. There's 5 technologies out there with variations in different companies doing low-power WANs, and I'll talk about each one of those. So if I will post this presentation, and I'm recording it, if it turns out, it'll be on my LinkedIn profile. So it's Ed Hightower. Just do a search for me on LinkedIn, and you'll find it. I'll post it out there this next week when I get a chance to upload it to Vimeo and connect it. These are, Google's my friend. There's a lot of great information out there from the analysts and researchers that are in the industry, and so I've used a lot of their stuff. So the first example of the Internet of Things, which we call it machine-to-machine just before now, but it's been called many things before that, but the actual first example was the telegraph. So in 1832, when the Germans created it, it actually caused something at a long distance to turn on, and then these guys got a response back. Well, Samuel Morse added the Morse code to it and became a very powerful communications tool, and was able to remotely monitor and control things. Oh, sure. Do we have USB plug in? So, all right. And Nikola Tesla, awesome guy, great visionary, an inventive mind. He actually predicted the Internet of Things because he said at one time, we will have devices that fit in our pockets and wirelessly control the world around us. Very prophetic person. So, in the past we've called Internet of Things and machine-to-machine, telemetry, SCADA, industrial communications, sensor networks, telematics. And we use various mediums such as wireline, microwave, private radio, Wi-Fi, satellite, and cellular to be able to communicate back and forth with these devices. So here's a formal description, definition of it. The Internet of Things is a system of interrelated communicating devices, mechanically and digital machines. Anyway, it goes into all this. What I say is IoT is about remotely monitoring and controlling equipment, devices. You know what's going on, make a decision, and you can control it. That's the basic idea. Remote monitoring and controlling. So, the Internet of Things is going to become the nervous system of the planet. With all the information that we're going to have collected and being able to process and use to our advantage, we're going to be able to create smart cities, smart distribution systems, optimize our transportation systems and our supply chains, and to create industrial Internet of Things capabilities we've never seen before. So, this is an inflection point. There's been many along the way. Andy Groves, who was a co-founder of Intel, wrote a book, and he talked about only the paranoid survive. And he gave examples of inflection points. And of course, when the integrated circuits, Jack Kilby right here at TI, when he first created the first integrated circuits, he changed the world because based on that, we now have all our microprocessors, microprocessing chips and things that we have now because of his development back then. Changed business, changed the way the world operates. Same thing, when they broke up the Bell monopoly, then it allowed the innovation of the telecommunication companies that we know of today to be able to prosper and create the things that we have, cell phones and all these different things. So then personal PCs came on board, the internet became available to the masses then in the 90s, and then in 2007 Steve Jobs changed the world with powerful computers in our pockets. The Internet of Things is going to dwarf that. We're predicting 50 billion devices will be connected soon. Probably not 2020. There's some reason why, and I'll tell you more about that in a moment. But at some point here in the near future, the next 5 years I'm predicting, we're going to be able to connect devices and objects in an economical way that we've never been able to do before. So the Internet of Things is a very complicated and messy, and there's lots of pieces to the puzzle. However, I break it down. If you understand these 3 pieces, I've been involved in wireless mobile data and machine-to-machine IoT for over 25 years. I actually sold a system down in Houston, Texas that was mechanical relays at the devices, private radio to bring the information back, and we translated information to put it into a mainframe. That was very archaic and very rudimentary, but it's still these basic parts. You have devices out there, you have some sort of connectivity, and then you have processing that takes the information in and does something with it. So what we've done is we've added technology at every one of these points along the way to improve the power, the capabilities, and reduce the cost. So I'm a wireless guy, so I'm going to talk about the wireless connectivity that's possible there. Now, in the past, various ways to connect those devices to the back-end systems was wireline and microwave, private radio. Cellular was very popular, particularly the 2G, the GPRS data networks that were out there. Then Wi-Fi and Zigbee, whatnot for short-range kind of stuff, and then satellite. The reason why those aren't going to be the predominant ways that we get the information is cellular is very expensive, it's very complex, it always will be. Now it's going to have a place. Those guys have a great footprint and coverage around the world. They will fit the bill for a lot of stuff. So it can be kind of like cellular and Wi-Fi. You use cellular where you need it, you use Wi-Fi where you can, to save you cost. So Wi-Fi, Zigbee, and other short-range technologies are going to be useful, but only for short ranges. It's very expensive to manage a very large network of these short-range devices. So that will never really be a solution for a lot of applications. Then you got private radio and microwave. And it's good for certain things, but it doesn't have ubiquitous kind of coverage. And then satellite. Satellites has great coverage, but it's still pretty expensive. That's changing. This whole thing is changing. So you need to keep on top of it and watch what's going on, because we're going to see new developments happening and things are going to become feasible that were not feasible or economical before. So stay tuned. Things are going to change. So I'm going to focus on the wireless part, and particularly on a segment called low power wide area networks. And these are just examples of some companies that are in that realm that are creating new capabilities, whatnot. Some of them have been around for several years, some of them are just getting started. So the definition or the characteristics of a low power WAN network are that they go long range, but they transmit at low power. By doing that, they save the battery. So some of these systems can last 10 years on a battery, the device running off a battery over 10 years. And there's a lot of applications where you want to put a sensor there and never go back if you can help it. Because they're nasty, they're horrible environments and whatnot. So if you can run off a battery for 10 years, all the better. You also, these systems lower the cost. Cellular is a very expensive infrastructure. If you can lower the cost of the infrastructure for these low power WAN systems, now you have an economic advantage over the cellular guys. Then the systems can be scalable, and that's one of the problems with some of these first generation LPWAN systems I'm going to talk about in a moment. They're not as scalable as they need to be. They need to permit mobility. So if your device actually gets moved to another device or another location, it needs to be registered then with that network that it's in close to or in coverage of. And then it needs to be reliable. Again, this is something that some of the LPWAN providers have problems with, creating a reliable connection. So if you look at the applications that are out there for IoT kind of things, this green is the cellular guys. They're going to have applications. People want that kind of worldwide coverage, be able to go from country to country and travel around and be able to talk anywhere and everywhere that there's an LTE signal. So they're going to have use. The short range, the Wi-Fi and the Bluetooth folks will have applications, particularly in the home. Anytime you're inside a building where it's easy to cover the area, then you'll have that kind of application. But many of the analysts say anywhere between 60 and 80% of the applications are going to be fulfilled by a low power WAN system. Another analyst says that 86% of all applications out there need 3 megabytes or less per month of information transferred from the remote device. So 3 megabytes, 86% of the applications, that's a huge requirement, a huge opportunity. And actually, if you look at this closely, you can't really tell very well, but 76% require less than 1 megabyte. So these systems don't need to transfer a lot of data. The cellular guys are great at transferring lots of data, particularly to our smartphones. And they're really focused really well on video and other high bandwidth kind of applications. But that's not what low power WANs and 86% of the and 76% of the IoT applications need. Just short messages. Lots of them, but short messages. So there's 5 companies out there: Sigfox, Ingenu, the NB-IoT from the cellular guys, LoRa and Ubiquin and Weightless that I'm going to talk about and compare and contrast a little bit. So Sigfox is probably the one that most people know about. They really did a great job. About 5 years ago, 4 or 5 years ago, they took a very simplistic or simple technology and they've marketed the heck out of it. And they've done a great job of getting people thinking about low power WANs and what's possible. So it's a first generation low power WAN. It is a proprietary protocol. It is a subscription model. So they're basically putting in a network and you have to subscribe to it. If it covers your area, great. If it doesn't, then you're out of luck. It is a very limited system. Being first generation and rushing it to market, they didn't do a whole lot of engineering and in-depth study on the thing and come up with any two-way kind of capability. So for the most part, it's mostly a one-way, from the device up-down, uplink is what they call it. And the downlink is sometimes not allowed or is restricted severely. And then it's imbalanced as well. So uplink is the most viable link. The downlink is not always going to be able to make a good connection. So you can't count on it for two-way. That hurts its reliability. It turns out that only about 10% of IoT applications need just a one-way communication. The other part about this is that Sigfox doesn't look at what's going on in the radio environment. It just says, I got an event that's happened here at my device. I'm going to send, and they send it 3 times. 1, 2, 3. They don't care what's out there. And it may or it may not get through. So reliability is a real big issue for them. However, doing such a great job at marketing everything, they have plans to put their network in 60 countries around the world, and they've already raised over $300 million in investment from people supporting them to build out their network. So they're doing something right on the marketing side. We'll see how their technology turns out. So they're deploying very widely. They've got a great momentum going for them. They've got some good players behind them, TI and Silicon Valley, Silicon Labs and that kind of thing. It's mostly one way, so they say power, because they're out listening oftentimes in some of their implementations. And it's pretty good for meter reading and for parking, those sorts of things where it's not really that critical if you get a reading once a month in a meter, or at least during that week of billing, you're happy with that. The other problem is that it's just if you're not inside of a coverage area for Sigfox, then you can't use their system. It's not going to be useful to you. There's a problem with security. Because it's mostly a one-way, we know, and we were talking about this morning, you need to be, as a developer, able to download some sort of update to your device, because there's going to be some need at some point, either a security patch or an update to the firmware to make sure that it is not susceptible to bots and to hacking and that kind of thing, turn it into a bot. So, let me tell you a little bit of difference. So, Sigfox is an ultra narrowband signal. So they put all their signals, see the spike there in the middle is an example of ultra narrowband or narrowband. You're putting all your energy into one small part of the spectrum so that you can punch through basically the interference and get long range for your system. The other is the bell curve here. The other approach to low power WANs is spread spectrum. So Qualcomm did spread spectrum during the Cold War. And they would hide the signal. It's actually been all the noise floor. They hide the signal. They spread it out over a large segment of the frequency range and encode it. The Soviets knew we were transmitting and they couldn't find it. They couldn't see it. They didn't know what was going on. Well, Qualcomm then evolved that technology and it became part of the cellular protocol called CDMA. And 2 guys out of them left Qualcomm and created another technology or another protocol for IoT, and I'll tell you about that in a moment. But that's the 2 approaches. Narrowband or ultra narrowband and spread spectrum. So Ingenu are these 2 engineers that left Qualcomm, and they said Qualcomm's gone on the path to help cellular companies continue to handle the wide bandwidth, the high bandwidth requirements of our smartphones. So that's Qualcomm. These guys left Qualcomm and said, we need to take this technology, but modify it to be able to support IoT. So short messages, but billions of them. But we're still going to hide it in the noise floor and be able to spread the signal out. So they created the company in 2008. They did a lot of testing, over 300 man-years of testing before they even went to market. And they had San Diego Gas and Electric as their first customer. They're helping them go through the proof of concept and all that. So their technology is great. They operate actually in the 2.4, the Wi-Fi band out there. And as we all know, that doesn't go very far. But they actually counter that by being have a diversity antennas. So they have 2 antennas in their devices on both ends. And because the spectrum and the coding that they can do in the, it's called spreading, they can actually get very good range and very good penetration at 2.4. So it's a very good technology. Highly secure, FIPS 140-2 and all that. And very good bandwidth for IoT type applications. So great technology. However, their business plan. They plan to put in a network covering the whole United States over the next few years. They're running out of money. They let their CEO go the end of June. And so they're regrouping right now, trying to find more money and or change their approach to the marketplace. Great technology, business plan isn't working out for them. But keep an eye on them. They may be something that may be revived and survive the next level. Cellular has many different protocols. And so this is just one of them. This is the low power WAN version of what the cellular guys are coming out with. So normally a protocol takes 8 years to get set, a standard to come out. Of the 3GPP group is made up of 800 of the cellular carriers and the providers to the carriers. They shortened that 8 years down to 1 year. To do that, they had to make a lot of compromises. They didn't do a lot of testing. The assumptions they made are using a very simplistic description of the radio environment, and they built their standard to deal with that. So right now they're beginning to install physical systems to test out to see if the spec and the theory works in the real world. So stay tuned. The other thing they did is that there's 2 major players supporting the low power, the NB-IoT, narrowband IoT standard, and that is Ericsson and Nokia and Huawei. They have 2 different approaches. They put both approaches in the standard. If you look at Nick Hunn, H-U-N-N, he has an article about this. He read the spec in depth and he goes, okay. What they've done is, to get it out in a year's time, they put them both in there. So right now, in this testing that they're doing, they're trying to figure out a way to make the 2 compatible. To do that, they're going to probably have to make the chips in the devices and the systems smart enough so they know which of the protocols they're dealing with. So the cellular approach will have worldwide coverage. The people that are very loyal and invested with the carriers will probably stay with the carriers, but it's going to cost them. So this complexity is going to be expensive to do, particularly when you have this kind of coverage that you're going to require. So they have their place. They're going to be a great supplier of solutions for certain things. And we'll see how it works out when they do all this testing in the real world. If it's really a good standard, then they have to modify it or come out with a new standard. LoRa is probably the most popular that has the best acceptance in the marketplace. So, okay. LoRa is, again, first generation. It was created by Semtech, and Semtech still owns the IP for the physical layer. The actual transmissions that are taking place over the radio environment is the IP is owned by Semtech. However, on top of that is the MAC layer, the layer that enables networking between the devices and the back end and the base stations and all. That is open source. So the business model for this, all the 3 before us were proprietary and subscription models. LoRa is you buy 1, 10, or 100 base stations depending on what you need. So you can put those in a campus or a region or a dock or wherever, and however many base stations you need to cover your area. Not trying to cover the whole United States or the whole world. You do it on an as-needed basis. They've got great response to that, and they built up a huge following and ecosystem. So it's a very good ecosystem, and it's been very good for people to get experience with using a wireless communication system to be able to talk to these devices. And theoretically, they have 3 different classes, so as they progress down the way, this is what I was talking about. Watch them because they're evolving and improving their spec all the time, and so it will get better. The shortcomings right now, though, is most all deployments are Class A. So nothing happens until the remote device has some event take place, and it needs to transmit up that something's out of limit, or something's turned off or turned on, or whatever the case is. Then it transmits up. Then it opens 2 windows to receive signal back that the signal has been received by the base station. Then it goes to sleep. The base station can never talk to that device again with a Class A device until another event happens. So it's not a very powerful two-way. You cannot reliably download security patches or firmware updates to the remote device with Class A. Now watch, they're going to be improving in the future, and they may be coming up with better ways to do it. I said the LoRa technology is the physical layer. LoRaWAN is the MAC layer that fits on top of the physical LoRa. That's the distinction. The LoRaWAN is open source, and it's made available to anybody, and they can modify it or use it as is. But several people have created their own MAC layer, their own LoRaWAN, if you will, to go on top of that. And they are finding ways to get around the shortcomings of the first implementations. But Semtech will always own the physical LoRaWAN layer of the OSI model. So that's one of their shortcomings, if you will. Decent technology, a lot of good response. They've done a great job of marketing. They've got a big ecosystem going on. It's proprietary. The downlink is limited right now. And one of the big problems is also the way it's set up with what they're doing and the way they're doing it now. When a remote device wants to transmit, it doesn't listen, it just transmits. And if it doesn't get an acknowledgement, it transmits again. When you've got a lightly loaded system, not very many devices in an area, you can live with that. It call aloha. It says, hi, I'm sending you stuff, hello, aloha. So as the coverage area gets filled with more devices, more of these devices start transmitting at the same time, and now you start having collisions. In some cases, it gets above 50% of collisions and lost packets. Now you put in another system, which this is all an unlicensed frequency band. People can put in multiple of these LoRa systems. When you start putting in multiple systems, now you aggravate the situation even more with more of this chirp technology, which is their spread spectrum version, starts colliding. So they have issues with that and the way that it's implemented right now. They may get solved with some of the new MAC layers, but we'll have to wait and see. I have been following this, so I've been involved over 25 years in wireless and machine-to-machine. I've been involved with weightless or low-power WANs for the last 4 or 5 years, and I've been watching developments going on there. The Weightless Special Interest Group, Weightless-SIG, is in the UK. They came out with their first spec called Weightless, now called Weightless-W for TV white space, almost 5 years ago. It is was the result of 7 years of testing by Ofcom, which is the UK's FCC. All that testing went in to create the spec they call Weightless-W, transmitting low power over TV white spaces. So if we're transmitting here in Dallas on channel 20 and channel 22, nothing's on channel 21, that's TV white space. In the US and the UK, we are now allowed to transmit on 21 in my example, as long as it's low power and does not interfere with the TV receivers on channel 20 and channel 22. However, only the US and the UK approved it. So it's been put on the shelf until other countries around the world allow that kind of protocol or that protocol to be used in the TP white space. But because of that, another company has been working in Taiwan with wireless communications that was limited, but it was decent. And it was talking to e-paper. So these are tags that go on the end of shelves into retail establishments or warehouses or whatever, and the wireless system would update the tags. They, in Taiwan, offered the technology, the IP, to the Weightless-P and said, we'll make it open source, you guys can add to it. So they took all the MAC layer that they created for the Weightless-W, added it to the basic physical layer that this Taiwan company into, it's on the next slide, to their MAC layer to create what they now call Weightless-P as in Paul for performance, basically. And Weightless-P is a high-performance, fully two-way system. I'm excited because it's like LoRa on steroids. And let LoRa may get there, but right now, this is open source. There's no proprietary issue to this. If you join the Weightless-P, just to keep them going, once you join, you have no royalty fees. So you can create base stations and radio modules based on this standard. Highly adaptive. It can go from 200 bits per second to 100 kilobits per second, depending on what the need is, what the environment is like, or what the data requirements are. It will modify the encoding scheme, so if you're deep in a building and it's not getting out very well, it will spread the signal out, slow it down, so you're adding latency, but you're trading that for the ability for it to get out of a deep building area where you might have a meter or some sort of other piece of equipment that you're monitoring. Well, highly adaptable. It is very flexible too. LoRa, Sigfox, all these are using the ISM band at 902 to 928. 915 is the center frequency, so that's in the US. In Britain and much of Europe, it's 868. This Weightless-P can operate in 169, 433, 470 to 512, and the 780 and 868 frequencies, etc. So it just depends on what your particular region requires as to what frequency band you go into with this protocol. It's relatively long range. LoRa has 150 dB link budget. This has 160 dB. So theoretically, any place that LoRa works, this will work and work maybe a little bit better. Ultra low power. When it's in standby state, it's less than 100 microamps usage. And as I said, it's very adaptive and everything. And the other great thing about it, now there's a long list of things that I'm not even listing here though. If you go and do a Google search on Weightless-P, then you can find out more of the details of other things. But one of the great things also is it's highly scalable. So I talked about earlier, as your network got densified with the LoRa network, then you had all these collisions. In the Weightless-P protocol, actually the base station goes around and says to each of the remotes, okay, you have a time slot, time slot, time slot, stop. I have an opening over here for anybody that needs to send me something before your time slot comes around. So it's a synchronized system. Then, not only do you coordinate so you don't have collisions, but also the power of those remote devices can be turned down. So you start out with a fairly large cell. If you need to densify it, and you basically, you can do 50,000 within this cell or more. If you need more than that, then you shrink the cell down by telling the devices, tune your power down, so you're going to talk less distance, but I'm going to put in more base stations around. So now you create small cells, like the cellular guys are doing, small cells that each have 50,000 devices or more in each of the cells. Very, very scalable system. And highly reliable. Every message that is sent up from the device is acknowledged. If it's not, then the device sends it again, but it's sending it under a coordinated process. So, and this is basically toward the end. It's fully bidirectional. Every message is acknowledged. Very, very adaptable. It's highly scalable, and it's an open standard. The problems are, Okay, I'm done. All right, this is the last slide. They just started shipping hardware 2 weeks ago. There's only one supplier right now, but it's open standard. There'll be other suppliers coming in, so you're going to have economies of scale and competition. So the price is going to start going down. You'll have other choices that you can make to buy, and the field tests are underway right now. These are all the slides. When you go to my slides, you can go to these websites and get more information for details. We put on a meetup. We have a website that sponsors or promotes and communicates the various IoT meetups. There's many of them that go on every month here in the North Texas area. If you do a Google search for IoT Texas meetup, then you'll actually be sent to this site, meetup.com/IoT Texas. Go check it out. There's 6 of us that are administrators. We post information about, this meeting was on that meetup site, and it's just one example of what the things that we post out there. I'm done. Thanks, guys.